We're very honored to have Diego Cordoba coming to speak to us from Madrid, and he's going to talk on the regularity of solutions for the Muscat problem. Thanks, Diego.
Thank you, Nathan. Well, first of all, I would like to thank Elena and Milton for this kind invitation. It's a pleasure to be in Rio. The dinner yesterday, fantastic. And as many of you know, I'm also relieved of not being this week in Madrid. Okay, so in the last years, I've been working with many friends in the problem of Muscat, and this past year we have obtained several results, and that's what I want to present to you. Okay, so this works. The first one is in collaboration with Peter, Paco Gancedo, Luis Rodriguez, and Bob Strain, and it has to do with global existence. So we had results of global existence in 2D for the Muscat problem, and we extend these results to 3D, and in this we realized that we could do a twist in our argument or 2D, and we got an improvement in the constants for 2D. So this is something I will show you later. Then there's another paper in joint work with Angel Castro, Charles Pfefferman, and Paco. And this has to do that we prove for Muscat the existence of splash singularities. And this type of singularities, CU mentioned them in her talk. It has to do that the interface self-intersects in finite time, and the curve remains smooth until the time of the blow-up. And this self-intersection happens in one point, and we proved this previously for water waves. And the argument, the proof, does not follow for Muscat, and one has to give another twist to the proof in order to make it happen for Muscat. And then for water waves, one can actually show that this self-intersection could happen on an arc of a curve. And what, in collaboration with my student, PhD student, Tania Pernas, we showed that this does not happen cannot happen for Muscat. Okay? So there's a difference there with water waves. Okay, so let me start by introducing Muscat. Actually, Muscat was mentioned first day by Vladimir in his talk. Let me state it again. I'm going to state it in a much simpler way. In my case, I'm going to try to make my life as simple as possible. And the porous media in which our fluids are going to have a porosity, constant porosity. Okay? So let me draw this thing again here so we can keep it in all the lecture. So let's say the entire talk is, I'm going to write everything in 2D, again for sake of simplicity. And I'm not going to consider boundary conditions. That makes our life much harder. So we are in R2, and we are going to divide the R2 in two domains, omega 1 and omega 2. And in each domain, we have a different fluid. And these fluids are characterized by so the notation is the viscosity and the density, and another viscosity and another density, and these are constants along the dynamics. And what separates one fluid from another is an interface, And I'm going to characterize this interface by Z and parameterize by alpha. So Z will have two components. And, of course, very important, gravity pointing down. And the problem is to understand the dynamics of this interface. So once we know how the interface moves, then from there we know the velocity field and the pressure in all points of R2. So the laws, since we're in a porous media, we are going to use the incompressibility condition, divergent free, the mass conservation equation, so the density is conserved along trajectories, and Darcy's law. Darcy's law, let me write it down here. Where we have viscosity, kappa is the permeability. I'm going to take it constant. Same constant in all R2. Pressure, G is gravity, and rho is density. Good. One point is that if we take rho 1 and mu 1 equal to 0, then I'm going to call this a fluid in the porous media, and the other part is not going to be a fluid. There will be a dry region. Okay? When you have a dry region, this is equivalent for water waves to have vacuum or air, or as you mentioned in her talk. Good. And in this case also, if we have a dry region, the pressure is constant along the interface. But if we have two fluids, the pressure is non-local and depends on both fluids. Good. So scenarios. So we were going to consider in three cases. Our interface is going to be flat at infinity, and also we can consider the periodic setting. So our interface will look like this. And also we can consider a closed counter. But the closed counter in this case is an unstable regime, no matter how you choose the constants rho and mu. So this is not going to be good for our theory. Okay, so let's write down the dynamics of the interface. Since we have Darcy's law, if we compute the curl in each fluid, we obtain that the fluid is irrotational. But there's a jump, and that will give us that our vorticity is a delta distribution. And I'm going to, my notation, the measure supported on the interface, I'm going to call it omega tilde, okay, or bar phi. And now we have an incompressible fluid, so we can write Biot-Savart law in all R2. So Biot-Savart law is giving the velocity in terms of the vorticity. Now this vorticity is a delta distribution, and we plug that in Biot-Savart, and we have this velocity field in terms of the measure and the curve Z. And this is defined everywhere except at the interface. So we would like to know what's the velocity at the interface. We take limits, and that will give us that the velocity, depending if you're coming from above or below, is equal to the Birchhoff-Roth integral, which is exactly this integral over here, plus a term that, depending if you're coming from above or below, it has a different sign. But this term is in the tangential direction, and that does not affect the dynamics of the interface. So the velocity is continuous in the normal direction, but is discontinuous in the tangential direction. Good. This will give us the dynamics of the interface, but in terms of the interface and this measure. So we want to close the system by obtaining another equation that relates, again, the interface with Barphy. And that's going to be obtained by Darcy's law. So we have the velocity in each domain. And what we do is that we hit with the tangential component, and then we add both equations that come from each fluid, and we obtain the following expression. The left-hand side, we have the velocity in terms of Birchhoff-Roth and the tangential component. The tangential component, since we're hitting with the tangential component, will give us this term. And the Birchhoff-Roth, we will obtain this other term. And the right-hand side, we have the term of the pressure, which is the difference of the gradient of the pressure in the tangential direction, which is equivalent to the derivative with respect to alpha of the difference of the pressures evaluated at the interface. And we don't have surface tension, so our pressures are going to be equal in the interface. So this is going to be equal to 0. And what we are left is with the component that comes from gravity, which is this one over here. Okay, so now this equation reduces to this equation over here, where A sub mu is called the Atwood number, and it's this relation of the viscosities. Barphy, the measure of the vorticity, and here is the G gravity, kappa is the permeability, C is a constant that depends on the difference of the densities and the viscosities, and the derivative of one of the components of the curve. Okay, so this one would like to invert this operator and have the measure in terms of our curve C. This was already studied by Baker, Maron, and Orszag. This is a smoothing compact operator in HS, and the adjoint operator of T is a Cauchy integral of the measure associated to the curve Z, and they computed the eigenvalues, and the eigenvalues are smaller than 1, as long as the interface does not self-intersect, and you have a smooth interface. Okay, so we can invert this operator if life is good, and this will be the equations of Muscat. Notice that this, which tells us the dynamics of the interface, is Birchhoff-Roth, and I didn't write down here the measure of the vorticity, because actually one can add any term in the tangential direction. And I always emphasize on this point because in our work, this has been a crucial point to choose the appropriate C to make our a priori estimates work. And then we finally have this other relation. So this is the system of Muscat. Okay, so this problem is well posed. as long as let me write. So if we start with an interface which is in HK, k bigger or equal to 3, so our curve is smooth. And F, this is the R-core condition. So it measures if our curve self-intersects or not. And this is what is known as the Rayleigh-Taylor condition. As CU has in her talk, she introduced this quantity for water waves, and it's also is the same quantity for Muscat. That the difference of the gradient of the pressure coming from both fluids in the normal direction better have a sign in order to have a well-posed problem. Okay, so let me give you a brief description why this works. And so we are going to use energy estimates. We are going to define an energy, and we are going to obtain a priori estimates. This energy is going to be the H3 norm of our curve Z and the R-core condition. First thing is to obtain bounds on this operator, because this operator is fine as long as your R-core condition is bounded and your curve is smooth, but it goes bad when these two quantities blows up. So one has to measure how this depends on this energy. And what one can prove is that you have this estimate, and this immediately tells you that you can control the H2 norm of the measure in terms of your energy. I wrote an exponential, but this can be also a polynomial of sufficiently big degree. So that gives you also a control of the Virchow-Roth integral in terms of H2. And now you look at the evolution of this energy. You compute all the terms, and all the terms are controlled by exponential or polynomial bound of the energy itself, except one term. And it's this term over here. K is a constant, and it's a positive constant. This term is bad because we have 4 derivatives of Z and 3 derivatives of Z, and our energy is 3 derivatives. So there is no way we can absorb this. And the only chance we have is that it has a negative sign. There's a sign involved. So if one uses this pointwise inequality, where lambda is the square root of the Laplacian, then it's very easy to implement this inequality here. You integrate by using the inequality, you end up controlling this integral by this term over here, as long as this sigma, which is the Rayleigh-Taylor, has a sign. And now you have here 3 derivatives, 1 derivative, but you integrate by parts, and you hit lambda on the Rayleigh-Taylor, and the Rayleigh-Taylor is of 1 derivative, so you're fine. So this almost closes the system, but now one has to make sure that your Rayleigh-Taylor does not go and becomes negative, and you measure how the Rayleigh-Taylor evolves in time, and that will give you, you control the minimum of the evolution of the Rayleigh-Taylor and you, in terms of this energy. And then you put both things together, and you have a time of existence in terms of your initial energy and your initial Rayleigh-Taylor condition. Okay, so that will give you local existence. So Rayleigh-Taylor plays a very important role. Is the difference of the gradient of the pressure in the normal direction. We can substitute what in terms of Z and Murphy, and is this expression over here, okay, where BR is the Virchow-Roth integral. So first thing, for example, let's get rid of this term. this is like by taking that both fluids have same viscosity, then the Rayleigh-Taylor simplifies to be this term over here. If we parameterize our interface as a graph, what it's telling us is that if your fluid above is heavier than your fluid below, then the Rayleigh-Taylor has the wrong sign. If it's the other way around, you have the good sign. So stable regime, unstable regime. So it's very clear. What happens if we have a dry region? Then we can use, as you already mentioned, the maximum principle for water waves. This can be also used in the for Muscat, and one can prove that in that case your Rayleigh-Taylor has a sign. So you're always in the stable regime. And now, if you have a closed counter and you integrate this, the Rayleigh-Taylor, it vanishes. So you will always have parts that are negative and other parts that are positive. So it will not be stable. Okay, so let me focus in both examples. So when the viscosity are the same, what do we know? So in that case, the equation that comes from Darcy's law reduces to this. So we don't have to invert the operator. The term that comes with the Virchow-Roth integral actually vanishes, and we have a explicit formula of the amplitude vorticity in terms of the curve. We plug that in our Virchow-Roth integral, and we have a closed equation for Z. I'm going to choose an appropriate Z and C in a term in the tangential direction, so that our equation will look like this. And I will explain why. And in the periodic setting, it looks like this. The reason to do this is that this C will allow us to choose a parametrization as a graph. So if you take your curve to be alpha f of alpha t, then this is consistent in the dynamics, and your Muscat equation reduces to this simple system. Okay, so once we have this, first thing to do is to linearize, and if we linearize, we obtain the heat equation, but instead of the Laplacian, we get the square root of the Laplacian, and we know how to deal with this, and it will depend what is the constant in front of the square root of the Laplacian. It has to have a sign, and that sign depends on the difference of the densities. And the Rayleigh-Taylor will look like this. Okay? So the Rayleigh-Taylor, as long as it's a graph, it will have the positive sign. But if it's not a graph, then it will have a negative sign. Okay, so Siegel, Kaflish, and Hovison in 2004, they show that the problem is ill-posed in the case when the densities, they worked in the case where the density were the same and had different viscosities. And they showed that the problem is ill-posed when you have the Rayleigh-Taylor with the wrong sign. We use their technique to do the case when the viscosities are the same and the densities are different. And this is ill-posed in the Hadamard sense. And the method to do this is to prove instant analyticity, since there is this square root of the Laplacian, and you prove global existence for the well-posed problem, and then you reverse time, and that's equivalent to be working in the unstable regime. Okay. Then recent work Well, Beck's also Wong prove a similar thing, but using different techniques. But again, it's a gain of analyticity. And Laszlo Shelkihidi studied in a different approach, and Felix Soto and previous authors introduced a notion of mixing zone. And so once you're in the unstable regime, and what Laszlo showed that if you take a flat counter with heavier fluid above, then for all time there's a mixing zone. Mixing zone, let me not give more details, but this is that you have a region where the density is the regional density, another region where it's the original density, and in between there's a mixing. But these solutions are weak solutions of the problem, and it's using convex integration. Okay, so how about in a stable regime? Remember that we're in the case where the viscosities are the same, and we have a graph, and our heavier fluid is below. So for the stable case, we can prove a maximum principle for the L infinity. The L infinity norm actually decays, and one can measure how it decays in the flat case, and in the periodic setting it decays exponentially. So the infinity decays, and we can obtain a very cute equality for the L2 norm of F, which is this one. And so the L2 norm of F decays, and you have this gain. This is like the derivative, so it looks like you're gaining smoothness in your equation is giving you for free a gain of smoothness of your function. So, but then we realize that this term is actually bounded by the L1 norm of F. So no hope there. Okay, so the question of global existence in a joint work with Angel Castro, Charles Pfefferman, Paco Ancedo, and Maria Lopez Fernandez, we showed that there's no global existence for all initial data. There exists initial data that starts as a graph in H4 that in finite time is not a graph anymore. Okay? So you lose your Rayleigh-Taylor condition. So that's what we call the Rayleigh-Taylor breakdown. Okay, so many of you already heard me explaining the proof of this. I'm going to be very fast to give you a sketch description for those who did not heard it before. This is so what the key here is not to look at the equation at the level of the function f. Is actually to go back and look at the expression in terms of z. And this is the expression, and then this is the key, is to find a curve, one curve, that will be the red one, which is a graph, but at one point in the center, the slope is diverges. Okay, vertical tangent at 0. And not only that, also the velocity above this point is pointing in one direction, and the velocity below that point is pointing in the opposite direction. So when you go forward in time, your graph red will become, in this case, when you go forward, it will become the green one, so it's not a graph. And when you go backwards in time, it becomes the blue one. This graph is the Rayleigh-Taylor. So the Rayleigh-Taylor is strictly positive everywhere except at this point 0, that is equal to 0. Okay, so once you find this graph, then can we use our local existence and then we're done? No, we can't, because we require in our local existence theorem that the Rayleigh-Taylor has to be strictly positive. But we can construct a curve which is real analytic, and then using Cauchy-Kowalskaya prove that the problems will pose forward and backwards in time. So that already gives you a real analytic curve that starts in the stable regime and in finite time is in the unstable regime. But we want to start with an initial data which is in H4. So how to deal with this? So we show that if you have a graph and your Rayleigh-Taylor is strictly positive, then you have instant analyticity. And if once you have, and how to do this, you measure the growth of the strip of analyticity. Now, this technique was pointed out by Marco in his talk, was done in the past for several authors, and Foya Santeman for Euler equations, and then many people in this audience has used this technique, as we heard, Igor, Vlad, Charlie, Edris, and Marco for Prandtl equation. Okay, so it is the same thing, and you look at the strip of analyticity, and you show that instantly your strip grows linearly in time, and then you have a control of how this decays. Okay, so how to prove the theorem now is we have these curves, the green one, the red one, and the blue one, and I go to the blue one and I make a perturbation in H4. So and I have a control of how this perturbation is, and that will be my initial data. Then this initial data is a graph. There's Rayleigh-Taylor strictly positive, and as time goes, it becomes real analytic. You have a control of the strip of analyticity, and once you have that, you have a control of how this strip of analyticity decays. Good. So what you do is you look at the difference between that curve and the curve that you know that and move from the unstable regime to the stable regime, and you show that a stability result for the difference. So you have a control. You can show that they are one close to another for a short time. But you have to make sure that this time is big enough that the curve that you know that turns has turned. And since the one is closer to the other one, it's as close as you want, then the one that starts with an H4 has actually turned to the unstable regime. Okay, so that will be the proof. What happens when you are in the unstable regime? Well, then your curve breaks down. So the theorem says start real analytic, it turns to the unstable regime, and then in the stable regime in finite time, your curve is not C4. Okay, and the proof of this is actually constructing in the unstable regime a curve which is real analytic everywhere except at one point, and at that point is not C4. Now you go backwards in time, and this happens in the region where it's unstable. When you go backwards in time, this region is the stable region, and your strip of analyticity grows. But your region where it's stable, your strip of analyticity decays. So you have to control the different parts of your strip of analyticity. And you make a perturbation along the curve that we actually know that turns from the stable regime to the unstable regime. So that's the idea of the proof. Okay, so if we add surface tension to this problem, the turning effect happens. The surface tension does not prevent this turning effect. But as was pointed out by Etcher and Simonet for small initial data and Ambrose for all initial data, this problem is well posed for surface tension. So if you have surface tension, you start at a graph and you pass to a non-graph, you're still in the well-posed world. Okay? And let me point out, this is a very interesting result by Rafa Granero and Javier Gomez, is that they studied the case of, let's say, you have boundary. So you have a strip in your porous media, you have two fluids, and you want to see if what happens with the turning effect. Of course, this same example that we constructed before, if you put boundary condition, but you put this boundary condition very far away, which does not affect the dynamics much, the dynamics of your interface, it will turn. But what they found is that they found an example of a curve that turns, but if you remove the boundary, it does not turn. So the turning is due, for some examples, to the boundary. Okay? Okay, so global existence results. Our previous result, this is for classical solution in H3, and we are going to require this smallness of this norm, where this is a Fourier transform. And our previous result in 2D was 1/5, and we have improved it to 1/3. And I will explain where's the key point of that improvement. And in 3D, this constant is 1/5. Now, notice that this constant is independent of any constant of the system. So gravity, viscosities, densities, permeability, this 1/3 is universal. Okay? So the idea of the proof is, okay, so we know there's a lambda, square root of the Laplacian hidden in the system. So we're going to add and subtract this lambda, and our Muscat equation becomes this dissipative term and this nonlinear term, which is exactly this guy. So we define this norm, and we show that if you look at the evolution of the H3 norm of F, this is bounded by a polynomial of high degree of the 1 norm times the norm 2 plus delta times the H3 norm squared. So if we want to have global existence, and we control these two, we finish. So by choosing the constant 1/3, one can see that this norm, the 1 norm, actually decays. And this is not a 1. This is a 1/3. Okay, I made a mistake there. So this is 1/3. So if initially this is smaller than 1/3, then you can guarantee that this fellow decays. And if it's smaller than 1/5, then you can actually show that 2 plus delta decays too. But if it's smaller than 1/3, then you can assure that the integral in time of F2 plus delta is bounded. Okay, so that allows you to close the estimate. Okay, and in 3D, I mean in another global existence result now is for weak solutions, and by weak solution we mean the usual. We multiply by a test function, we integrate, and we hit all the derivatives in our test function, and we define our weak solution to satisfy this for all test functions. And what we show is that if initially our interface is bounded and the first derivative is smaller than 1, this is for 2D. For 3D, you require 1/3. Then you have global in time weak solutions, and in particular, these solutions are Lich's. The key of this proof is that one can get the maximum principal for the derivative of f. And if in 2D, if this initially is smaller equal to 1, you can guarantee that the evolution of the maximum of the first derivative decay is the derivative is smaller than 0, so it cannot grow. And then the proof that you regularize the system, and you have to regularize in such a way that these two quantities, the L infinity norm of f and the L infinity norm of the derivative, have the same property, and you have to regularize in a way that you have global existence, and then you show a strong to show that the limit will become a solution of your equation in a weak sense. Okay, so that's the part of global existence. So now the part of a splash. So we are in the dry region. Mu1 and ρ1 are equal to 0. And so the Rayleigh-Taylor is always positive. And we prove, and we define that the splash is a curve that self-intersects where this curve is smooth. And what we show is that this actually happens for Muscat. So let me compare this with water waves. So this was proven in collaboration with Angel Castro, Charlie, Paco, and Javi Gomez for water waves. And Daniel Kutan and Steve Scholar extend this result for solutions that are not irrotational. And we were able to prove also that the splash singularity, and again, a splash singularity is when the interface collapses along an arc. So you can have and that happens for waterways. And then Charles Pfefferman, Alex Ionescu, and Victor Lee showed that if you have two fluids, then a splash cannot occur. How does it work? Well, in order for, in my notation of the dynamics of the curve, in order for a splash to happen, if a splash happens, then the measure, the bar phi, the amplitude of vorticity, has to blow up at the point of the splash. Okay? So this was proven rigorously by this team, and they also show that if you have two fluids, the amplitude of a vorticity, or this measure, has to remain bounded. So if it remains bounded, then the amplitude of vorticity cannot blow up. There's no splash. Okay? So that's their proof. Okay, so in the case of Muscat, if you have, for example, the simple case where the viscosities are the same, then the density is, the vorticity is equivalent to the difference of the densities for. So if your curve is smooth, you have a splash, your vorticity has to remain bounded. So therefore, by their result, if the vorticity is bounded, then you don't have a splash. Okay, so for two fluids, in Muscat, in the case of two fluids, you cannot have a splash. Then Bob Strain and Paco Gancedo proved a similar result, but not with a different way, just looking at directly at the formula for F. And they were studying two interfaces, and they showed that the distance between the two interfaces cannot reach 0 if the curves are smooth. Okay, so how to prove the splash? So here is our initial curve, evolves, and it collapses. So the idea for water waves is to actually, in the case of the red, we have the amplitude of vorticity equal to infinity, so it's not well defined, so we cannot even write the system of equations. So what we do is a conformal map, and which is, and this map is exactly equal to this. That means that the square root of the branch right here opens up the splash. So the branch actually is a line that crosses these 2 points here. Okay? But in this new framework, our curves are smooth and they do not self-intersect. Okay? So the proof for water waves is to prove local existence in this world and go backwards in time. Equations for Euler are reversible in time, and that will give you a proof of formation of splash. But for Muscat, it's not reversible in time. So what we do, we make this transformation, and we have the system in this new domain where the Arcor condition is satisfied, and what we do is we prove that the problem is well posed in this new domain, but we cannot apply, we cannot go backwards in time. But what we can do is we prove a stability theorem. We show that if two interfaces are very close, they will remain very close for a short time. So if we choose an initial data, and here's the branch. In this world, we choose an initial data where the velocity at these 2 points are pointing in this direction. In this world, we prove a stability. So if we have a curve which is very close but does not touch the branch, we know that they will remain close for a short time, but since they're short existence, and then for a short time this has crossed the branch, and this one has crossed the branch too. So you go back to your original domain and you have shown that this one has self-intersect in finite time. And the result with Tanya, that there's no splat singularity, that's is because the equation, you have instant analyticity. So what we prove is that in the omega tilde domain, your curve starts in H form, it becomes real analytic instantly, and then you measure how the strip of analyticity decays, and you show that this decay depends on the Arcor condition and on the smoothness of the curve. So if you assume that you have a splat, then your curve will remain up to the splat, real analytic, because in this world the Arcor condition is bounded and the smoothness is preserved. When you go back to the original domain, you have a contradiction. You cannot have two curves that are real analytic to intersect in an Arcor and in an arc. Was that clear? Okay, thank you.